Okay, thanks everyone. Welcome. Thanks for joining this talk with me. This actually started as a curiosity of myself. So just to be sure, because the whole day is focused around how can we use LLMs, how can we use AI. I love the technology. I use it every day. It's not meant as like a negative talk towards LLMs and no one should use it. So that's not it. All right. So, what is it about? I'm just going to tell you, be critical of everything that I say. I myself am very critical about this because it's quite hard to find good information on this. All right? So, why was I curious about this? Well, I saw all these articles. So, it uses as much energy as a small country. It's only the beginning. AI and energy. Will it reduce emissions or increase the demand? Well, there are a lot of articles about this. There's a yellow one, just so it's nice. Yeah. And then I saw that one. That one was the one that actually got me curious about it because I saw, whoa, that's a lot of money they invested in nuclear energy. Does it really take so much energy to use the LLMs on a daily basis? So basically, I want to ask you a question. I've made it interactive. Everyone loves this, but I'm going to reinforce you because I have eyes. If you guess it correctly, I will throw you an eye. You can eat them. It's chocolate. It's very nice. All right? So, how much energy did it take to train GPT-4? How many times could you fly from New York to London for the same amount of energy? Anyone, just shout. You don't have to. 200. Anyone else? 2,000. 4. You're closest, so you get an egg. It's 2.5. Oh, sorry. That's really bad. Okay, so next one. You could drive how many times around the Earth in a Tesla Model 3? Just shout. Anyone? It's chocolate. How much? 1. Anyone else? 5? 35? 2? Anyone else? Okay, you get the egg. It's 205 times. Sorry, my aim is really bad. Maybe I should have practiced that more. All right, last one. This could power how many houses for a month? Average US electricity. 300. You like the egg? You want another one? Anyone else? 300. Oh, it's 1,500. You get the egg. It's fine. There you go. Okay, so it actually took around, I'm just going to skip through this. It took 1,287 megawatt hours. That's this big number that I came around. But every time that I get a number like this, I think, what does it even mean? I have no feeling with this number. Does anyone have a feeling with this number? No, it's hard, right? So my goal was to research just for myself because I was curious, what would it mean to adopt LLMs in our everyday life in terms of energy usage? Okay, so what will be in this talk? I will have a small note on the energy metrics that I use for this. What uses energy when training and using LLMs? A bit more like on the hardware side. I was curious, like what's exactly the energy? It's going to be really short. Training versus inference energy usage. What's the difference about that? What would be the implications of adopting LLMs in everyday usage? And how does it relate to the technology industry that we're all working in, most of us? And how does it relate to the world energy usage? So that finally we could get some feeling for this number that seems to be very big, but I don't really know. Okay, so a note on energy metrics. I came across at least these 3. There are much more, but we have like the watt hours, the kilowatt, megawatt, gigawatt, terawatt. That's foreshadowing about how much we're going to talk about. We have flops, sometimes per watt. How many calculations can we do per watt? I didn't choose for this one because it's more about the efficiency, not as much about like how much it's actually using. And then there's, of course, how much carbon dioxide is released. I also choose not to focus on this one because that's also dependent on how you generate the electricity and everything. Oh, sorry. So I chose to do like just on the watt-hour side of things. That's how I will. That's what I will use for everything. So that's a small note on this. So what uses energy? Well, I'm going to exclude the fabrication of CPUs, GPUs, data centers, and everything. So building the stuff also costs a lot of energy. I'm not going to talk about that, okay? What I will talk about is 2 important moments of energy usage, training and inference. So what uses energy when training an LLM? Well, it's not that surprising, really. We have storing data, so we need to store a lot of text data. Of course, we read about that social media have a large data centers. It costs energy to store all these images and photos, so there's a part about this. Moving data through RAM to GPU, we're training on a lot of GPUs. It takes energy to move that data through the systems every time during training, right? Makes sense, okay? So actually what's happening, we have this text data, it's in the end it's all 0 and 1s, right? It's electrically charged and we need to move it, so we're sending electrical signals representing those patterns of our data. We need to send them to wires through the RAM and then through the GPU. And those electricity signals, that's in the essence, that's what's causing energy when moving data, right? Makes sense. So then we have to perform many float computations on GPU, also not that surprising. So GPUs are built with transistors, and in the end, there are also like electrical signals moving and doing these computations. So it's these electrical signals that use energy on the GPU, and then we have the cooling of the GPUs and the data centers, which is also a significant one. So I have a question: how much percent? You can exclude the fourth one. How much percentage of the energy usage goes to the GPU computations in percentage? Anyone has a guess? You can exclude the cooling. I'm not taking that into account. I had 80, and what did you say? 60? Anyone else? 5? 95. Oh, sorry. Okay. Well, I have to give 2x because it's actually 70%, around 70%. Who said 80? You did? You get an egg. Sorry, and you get an egg. Oh. Well, it's one of the better ones. Okay, nice. So, and then the moving data through RAM through GPU roughly takes 20%. This was a bit hard to find out. It's a bit debatable. I saw some different numbers, but this is what I came across. It's around this range, probably. Okay, and actually, the storing the data, having it at rest, is negligible compared to like the other two. Okay, so that's what we're talking about. Then, so this is for the training, right? But we also have the inference. Well, it's pretty much the same. We have to move the data to the GPU. We make an API request, so these signals get there. We have to move the data on the GPU. Then we have to perform many float computations on the GPU. Is that it? No. And we have the cooling of the GPUs and the data centers. Those are basically the same, but we have less data moving that's happening during inference. Well, there's still data moving, but it doesn't come from like a source where we iterate over the data set time and time again. Okay, so this is what I want to talk about, and then I want to compare like the training versus the inference energy usage, okay? So remember, training took 1,287 megawatt hours of GPT-3, okay? First days of ChatGPT, we had 10 million requests per day. How many megawatt hours did it take on launch to run ChatGPT per day? Give me a number. You can earn still X. I have still some fuel left. 300. How much? 300. Anyone else? 10? 50? You're exactly right. No, it's not exactly right. Sorry. It's 29, but you get an X. Close. Okay, 29 megawatt hours a day. Okay, first days of usage. In February 2023, an estimate was made that it required 28,936 GPUs, which came to a total of approximately 564 megawatt hours per day to run ChatGPT. February 2023. All right? It's an estimate. We don't actually know these things, so be critical, all right? But this was an estimate that was made by various sources on the internet. On August 29, 2024, OpenAI announced that ChatGPT has 200 million weekly active users. So, just ballparking, we have roughly 500 million requests per day that are being made. You could argue like lower and higher for this, but just for the idea. This would mean that we use roughly 1450 megawatt hours per day for ChatGPT running it. So from this we can see, actually the inference is by far the thing that takes the most energy after deploying such a model. Okay, that's the main gist that I want you to get away with it from this. All right. So, what would be the implications of adopting these LLMs in our everyday life? Well, most of you, if you're like me, are programmers, so what do we do the most? Googling. I'm going to talk about Googling, I'm going to talk about coding, and I'm going to talk about office work. And these are things that I made up, these things, just to like play with the idea of how much energy would this use. And mainly also think about all the other things that are being built with LLMs right now, the agentic workflows. I'm not even going to talk about those, but we can imagine all these kinds of implications where LLMs are going to be used in our everyday life, right? So, about Googling. How many watt hours does it take for one Google search? Hit me. 5.1? You're actually pretty close. It's 0.3. So it's really nice. It's getting really better. You see that? Okay, so we have roughly 8.5 billion searches per day, which means Google uses 2.55 gigawatt hours per day. So I had to Google what the order was of mega, giga, tera, but it's mega and then comes giga, okay? Just, I'll have a picture later, so if you forget, just like me. Okay, so then, oh, I spoiled it, but what, what does it take to do one ChatGPT query? On average, it totally depends on your question and how many tokens you generate, but on average, it's 3 watt hours, so it's 10 times as much, roughly, okay? This estimate was made on like a period where they counted the request and the total energy usage and they just divided it. So it's an estimate on average, right? So then it's not hard to see it. Suppose, like Bing, we generate an LLM answer every time we do a Google search, we would get 25.5 gigawatt hours per day, which we would use just by using the Google function, which is a lot. That is really a lot. So if we go to coding, I've used Copilot. Who of you have used Copilot? Nice. Okay, cool. So suppose I have some code, all right? This is roughly 426 tokens, this piece of code here. Suppose I want to test another thing. This test file, I'm going to say like, oh, Copilot, write me another test, right? Okay, so on average, this from other source, we use, ChatGPT uses 1.9 watt hours per 1,000 tokens, okay? Suppose we use 600 tokens on an average query. And for this, I use like, these are the input tokens, and it's going to generate another, I don't know, 150 tokens. It's ballpark, but roughly 600 tokens on average, right? So that would mean we would use roughly 1.14 watt hours per Copilot suggestion. Suppose we do 4 suggestions per minute. Copilot suggestion is, maximum limit is I think 5 per minute or something, and they have a limit, but this was roughly around what they expected from their usage. Suppose, this is ambitious, but you work 5 hours a day and you're coding. We do 1,200 suggestions per day. This would mean that we use 1.37 kilowatt hours per day per developer using Copilot. They have 1.3 million subscribers as of, I don't know when it was. It was 2023 or something. That would mean they would use 1,781 megawatt hours per day. The developers using Copilot. So it's not all the other code completion models that are out there, just the Copilot ones, okay? Next one, office work. I have this email. Suppose that Google and Microsoft both decide we're gonna generate sample responses, initial responses to emails for users which you can edit. We offer that functionality. This is ambitious because I don't think this is really something to do, but just for the idea, right? This is 207 tokens, this email. We have the same amount of watt hour per tokens. Suppose we then use 300 tokens on an average query. So we also have, I don't know, 100 tokens on an output device. So we have 300 tokens on average. We have this many watt hours per mail. This was what I found on the internet. Is there anyone who sends 40 mails a day or more? No, right? Okay, thank goodness. Because then I said, let's do 20 mails per day. Is there anyone who sends 20 mails per day? Because I don't, but I felt already like going in against the statistic I found. But okay, let's say 20 mails per day, okay? Okay, just bear with me for the idea. We have 11.4 watt hours per day. Then we would get, I don't have this here, but I have this made the assumption that there are 1 billion people that send mail, okay? Then we get to this amount of megawatt hours per day. That's also huge. So, I wanted to make one extra note on images because I'll alert you here with generative AI and I'm only talking about like text. So I'm going to put one slide with images here and that's what you have to do with. But why I wanted to do that is because this was a paper, this is a really great paper by Hugging Face where they analyzed the cost of generative AI applications. We see here different types of Gen AI tasks and you see image generation is really the one that takes a lot more energy than the text generation we've been talking about, okay? And roughly 1 image equals charging 1 phone, on average. Okay? So it's also something to keep in mind. So suppose we have a Copilot which just starts, everyone can start generating images. That's quite a big energy demand that we're putting out there, right? So how does it relate to the technology industry? Like LLMs, AI, it's nice, but we have a whole industry doing a lot of stuff with data centers and everything. How does it relate to it? Well, we had the Googling thing. We have 25.5 gigawatt hours per day, 9.1 terawatt hours per year. What that mean? Okay, just times 365. The same for the coding with Copilot. We would get that amount. And then we would have the mailing, which would amount to 4.16 terawatt hours. Okay. This is, by the way, by the assumption that everyone codes 7 days a week, which is fairly right, I think. So Google and Microsoft both use how much terawatt hours in 2023? Anyone? 500? 12, 50? Sorry? 25. Okay, you're very close. You're getting this. Okay, maybe I could pass. Sorry for the headshot almost. But okay, 24 terawatt hours in 2023. Okay? Ireland and other small countries use roughly 31 terawatt hours of energy in 2023. So Google and Microsoft, they both use this. They are comparable to small countries in terms of energy usage, right? But we also, the ICT sector, I will save you this one. It used 915 terawatt hours in 2020. Why 2020? Because I couldn't find the one for 2023. So we'll have to take some steps back in time. But just for like the idea on the scale that I think it's growing about 2% per year over the past 3 years on average. So it will be a bit bigger now, but around this. So that would then mean that the above 3 implementations could already increase the ICT energy usage with 1.6%. Okay? And remember, be critical about what I say, because everything is based on a few numbers that are reported, right? So still be critical, but this is the way of thinking that I apply to this. Okay, that's still a lot. How does it relate to the global energy usage? That's the promised chart. We have kilo, mega, giga, tera. Okay, we will only go to tera. We will leave the peta and the exa alone. Okay, so global energy usage. This is the last one. You can earn one last egg. Anyone wants to take a guess? It's it might be tricky here. 2,000? 2 billion? 50,000? 60. Okay, you're closest. It's 100,000 more. I found 2 numbers, but it's around this range. I think the first one was for 2019 and the other one from 20. I think you're gonna get an egg. You're really far away, so I'm gonna try this. Yeah, that's a good idea. I'll take it. It's okay. Thank you. So we have this as a global energy usage. Data centers and communication networks account for roughly 2 to 3% of global electricity consumption. This was before the AI. This is also 2020, something around this year, that year. The 3 use cases we talked about would mean an increase of 0.009% on this energy usage. Okay, this was in the end the answer I was looking for to get a feeling for what would it mean to implement LLMs in ID. Okay. Just to give an idea, what's the energy, like the global energy usage going to? If you've never seen this before, this might be interesting. It's going to a lot of residential, so this buildings and heating of buildings. We have a lot going to transport and manufacturing. It's really a lot. Services, a lot of things fall under here, and this is the other industries. And so we're talking about the industry. The data centers is like 3% of this, and it's in there. Okay, just to give an idea of where everything's going. So, what are the takeaways from this talk? Well, LLMs use a lot of energy. Well, big surprise. Inference uses much more energy than training. And it could have, I think, a significant impact on the energy use of the complete sector. That was what my conclusion was. I'm curious if I convinced you. No, that wasn't convincing, but if you agree with me, basically. But what are some disclaimers that I really wanted to give you, because this is at least how I could be very critical of this. For newer models, there's very few information. I've talked about GPT-3. I have no idea how it is for GPT-4o. I have no idea if it's more. Oh, I do it again. If it's more or if it's less, I don't know. I don't know if it decreases, if it increases. There's just there's not much information about these models. There was Hugging Face research that I saw came through this week that reduced like the parameters of Llama 3 with 50% and kept 98% of the accuracy. So we're living in a time when like in a couple of months there could be something that completely changes the industry. Like, and I think that will be the case. That like in a couple of years we can run large language models in much smaller ways, much more energy efficient. Hardware is constantly evolving, of course. Technology initially always uses a lot of energy. This has always been the case. But when I was Googling this, I also came across a Jevons paradox. I don't know if you know it, but it's basically what it says is governments have always assumed that, but we will get, it will get more efficient, so the energy use will increase, but because it decreases, there's a much more increase in demand. So historically, it also has shown that in the end, we still use more over time than that we actually decrease it. I don't know, I just came across, I put it in there for if you want to check it. So how much energy was used for this presentation? I thought it would be nice to disclose, right? Okay, 22,834 tokens plus one phone charge, because I tried to generate one image, but it wasn't satisfied with it, so I didn't put it in there, but I did do it. So 30 watt hours in total. That's not that much then. It's around, for the idea, I think it's 6 phone charges, something like that. I don't know, around 6 phone charges. Okay, just because I talked with the AI, I was in the car and then I talked with GPT. Well, anyway, so what do I in the end want to say with this talk? Well, I'm not against using LLMs. I think they're really great. I just think it's important that everyone has like a feeling for what's the impact if I choose to do this with LLMs. And I think in the end, everyone has to make that decision for himself or herself. And I think it just helps if you have a bit more information on like the other sides of LLMs. So, questions and cool stuff. These are the 2 papers that are really great that I used, that I thought were the best out there right now. And Code Carbon is a tool with which you can track the CO2 emissions of your program. It's also really cool. So, thank you for your attention.